Now that we know what relations are, hopefully, we will now talk about properties of relations. So relations can often have certain properties, which we're going to discuss. So first, the definition. Suppose R is a relation on set A. We say that R is reflexive. That's what we want to define. What does it mean to be reflexive? So R is reflexive if for all x in A, x is related to x. Okay, this is saying that the relation is reflexive if it relates every element of A to itself. For example, here we're going to see a bunch of examples of relations on Z. These are all relations on the set of integers. Remember, we've seen in the, we've seen one example of a relation on a Z. We saw the example of, in the previous video, an example of a relation on Z. So here we're going to see a few more relations on Z, and for each one, for each relation, we want to determine if it is reflexive. So let's consider the relation less than. So this is a relation on this set of integers. It tells you whether or not one integer is less than another integer. So is this relation reflexive? So this relation is actually not reflexive. And here's why. So for example, if I tell you 3 is less than 3, that is false. If this relation would be reflexive, what that would mean is that for all x in A, x would have to be related to x, meaning it would have to be true that 3 is less than 3. And it would have to be true that 4 is less than 4, and 5 is less than 5, and so on. But we know that's not true. For example, we know that 3 is not less than 3, right? If I tell you 3 is less than 3, that is false. So therefore, this relation, this less than relation, is not reflexive. It's a relation, but it's not a reflexive relation. It does not have the reflexive property. Let's consider another relation. How about the relation less than or equal to? That's a relation on, again, it's a relation on the set of integers, set of all integers. So it tells you whether or not one integer is less than or equal to another integer. So is this relation reflexive? It is. Why? Since for all x in Z, right, for every integer x, x is less than or equal to x. This is a true statement for every integer Z. Again, for every integer x. Take any integer x, it's always going to be true that x is less than or equal to itself. So since for all x in Z, x is less than or equal to x, therefore, this relation, the less than or equal to relation, is a reflexive relation. Another example. How about the relation equals? We've seen this relation before. The relation equals, this is a relation on Z. This is also reflexive, since for all x in Z, x is equal to x, right? No matter what x is, if x is an integer, then x is equal to x. So the relation, the equals relation, relates every integer to itself. Therefore, the equals relation is a reflexive relation. Another example. How about the relation not equals? So this is a relation that indicates that one integer is not equal to another integer. So is this relation reflexive? It is not reflexive. For example, 3, if I tell you 3 is not equal to 3, that is false. However, if this not equal to relation, if it would be reflexive, then it would say that 3 is not equal to 3, and 4 is not equal to 4, and 5 is not equal to 5, and so on. But we know that's not true. For example, we know that 3 is not equal to 3. We know that 3 is equal to 3. So we know that if I tell you 3 is not equal to 3, that is false. So therefore, this not equals relation is not reflexive. Again, this relation, which describes not equals, it is not reflexive. Another relation. How about the relation does not divide? Again, does not divide, right? So this indicates whether one integer does not divide another integer. So for example, 5 does not divide 3. Anyways, this is a relation. It's a relation on the set of all integers. Is this relation reflexive? It is not reflexive. Since, for example, if I tell you 3 does not divide 3, that is false. If this relation would be reflexive, then it would say that 3 does not divide 3, and 4 does not divide 4, and so on. But we know, as a matter of fact, that 3 does divide 3. So if I tell you 3 does not divide 3, that is false. So therefore, this relation that does not divide a relation, this relation is not reflexive. Okay, now let's talk about another property of relation. So we talked about reflexive. Now let's talk about the symmetric property. So again, suppose R is a relation on set A. We say that R is symmetric if the following is true. If for all X and Y in A, if X is related to Y, then Y is related to X. Right? So, this is saying that whenever one thing is related to something else, then that second thing is related to the first thing. So whenever X is related to Y, then Y is related to X. If you have if a relation has that property, then this relation is symmetric. Okay. You can think of symmetric relation as a two-way street. You can get from one to another. You can get from one end to another end, and from get from end A to end B, and from end B to end A. So for example, consider the following, again, the same relations on Z, and for each relation, we want to determine now if it is symmetric. It's going to be the same 5 relations. So here's the relation less than. Is it symmetric? So it is not symmetric. So remember, actually, yes, it is not symmetric. It is not symmetric. And here's why. Since, for example, 3 is less than 7 is true, but 7 is less than 3 is false, right? 3 is less than 7, but 7 is not less than 3. So if I tell you, so this if then becomes false, right? Because here we have an example where the if part is true, right? X is related to Y, 3 is less than 7, and yet this part is false, right? 7 is not less than 3. Again, here X is 3, this is our X, and this is our Y, and then again, this is our Y, and this is our X. This is our X. So the if part is true, right? X is related to Y, 3 is less than 7. However, the then part is false, right? Because 7 is not less than 3. This is false. Now, what happens when you have an if then, right? What happens when you have a conditional statement where the first part is true and the second part is false? Well, if you remember, the entire statement is a false statement. So this shows that this relation is not symmetric. How about the relation less than or equal to? Is this relation symmetric? Once again, no, it is not symmetric. Since, for example, 3 is less than or equal to 7 is true, but 7 is less than or equal to 3 is false. So again, we have the if part is true, but the then part is false. So what we did basically here is we gave a counterexample to this, right? We gave a counterexample to the symmetric property, which shows that for this particular relation, we don't have the symmetric property. How about the relation equals? Is this relation symmetric? It is. Why? Since for all X and Y in Z, so we have to show that if X is related to Y, then Y is related to X. Well, let's see. Well, if X is equal to Y, this relation represents equals. So if X is equal to Y, then Y is equal to X. That is true. That's always true, no matter what X and Y are, no matter what integers X and Y are. If X is equal to Y, then it is definitely true that Y is equal to X. So the relation equals is symmetric. How about the relation representing not equals? is this relation symmetric? So remember, this relation was not reflexive, but that doesn't mean anything regarding symmetric. It could either be symmetric or not. So which is it? Is it symmetric or is it not symmetric? So it actually is symmetric. Remember, it was not reflexive, but it is symmetric. Why is it symmetric? Since for all x and y and z, if x is not equal to y, then y is not equal to x. So in other words, this property holds, right? For every possible integer, if x is related to y, meaning if x is not equal to y, then y is not equal to x. That is true. How about the relation does not divide? This relation representing does not divide. Is this relation symmetric? So it is not symmetric. Since, for example, 6 does not divide 3 is true, right? It is not true that 6 divides 3. Again, 6 does not divide 3 is a true statement. Okay, think about it. 6 does not divide 3. That's true. However, if I tell you 3 does not divide 6, that is false. 3 does divide 6. So what do we have here? We have here a case, what I've just given you is a case where the if part is true, right? 6 does not divide 3. That's the if part, that's true. And yet 3 does not divide 6 is false. So the then part is false. So this is the counterexample, and it shows us that this particular relation that we're dealing with, this fifth relation here, this relation is not symmetric. Okay, so we had one property reflexive, another property symmetric, and now we have a third and final property, which is transitive. So again, suppose R is a relation on set A. We say that R is transitive if for all x, y, and z in A, if x is related to y and y is related to z, then x is related to z. Again, this property claims, this property says that if x is related to y and y is related to z, then x must be related to z. Okay, so some relations will have this property, some won't have this property. We'll see some examples. So again, we're going to talk about the same relations, and for each one, now we're going to ask, is the relation transitive? So how about the relation less than? Is this relation transitive? It is, since for all x, y, and z that are elements of z, meaning take any integers x, y, and z. Take any integers you want, 3 of them. They could all be the same integer, by the way. They don't have to be 3 different integers. They could be the same, they could be different, doesn't really matter. If x is less than y and y is less than z, then x is less than z. That is true. Again, no matter what these integers are, if it is true that x is less than y and y is less than z, then we know for sure that x must be less than z. So therefore, this relation passes the transitive property. It has the transitive property. How about the relation less than or equal to? Is it transitive? Yes, it is. Since for all x, y, and z that are integers, if x is less than or equal to y and y is less than or equal to z, then we know for sure that x is less than or equal to z. So therefore, this relation is transitive. How about the relation representing equals, the equals relation? Is it transitive? Yes, since again, for all x, y, and for all integers x, y, and z, if x is equal to y and y is equal to z, then x is definitely equal to z. So that is true. So again, it passes this test, right? This test says for every element of A, in this case, for every integer, for every integer, if x is related to y and y is related to z, right? So if x equals y and y is equal to z, then x is related to z, meaning x is equal to z. And that is true in the case of this relation. So therefore, this relation is transitive. Next example, how about the relation not equals? Is it transitive? So it is not transitive. Since, for example, this is true, right? If I tell you 3 is not equal to 7 and 7 is not equal to 3, that is true. However, is it true that 3 is not equal to 3? No, that is false. Notice what we have here. This is our x, okay? This is our y. This is our y again. Again, we have x, and then the y, and then the y, and then the z. So this is our 3 is our x, 7 is our y, 7 is our y. And here for z, we use 3 again. We're allowed to do that. Nothing told us that x and z are different. We're allowed to have x and z be the same number. So again, x is 3, y is 7, and z is 3. Now, this is true, right? So we have the if part is true. X is related to y, and y is related to z. 3 is not equal to 7, and 7 is not equal to 3. But what about the then part that says x has to be related to z? Is it true that 3 is not equal to 3? No, it is actually false because 3 is equal to 3. So we have found a counterexample for the transitivity property on for this particular relation. So therefore, this relation is not transitive. How about the relation does not divide? This relation representing does not divide. So it is not transitive also, since, for example, if I tell you 6 does not divide 10 and 10 does not divide 24, that is true. So the if part is true, but the then part is false. 6 does not divide 24 is actually false because 6 does divide 24. Okay, so therefore this relation is not transitive. More examples. So let's say we have a set A equal B, C, D, E. Okay. Consider the following relation on A. Call it R, and it has the following pairs. All right, so that's R. It has a bunch of ordered pairs. Now, let's ask, is R reflexive? So in order for R to be reflexive, we would need to make sure that for every element of A, there is an ordered pair that corresponds, there's an ordered pair containing double of that element, meaning, so you would have to have B comma B, which we have, C comma C, which we have, D comma D, which we have, and we would need to have another pair E comma E, but we don't have it. So R is not reflexive since E is one of the elements of A. However, E is not related to E. There is no pair in R, E comma E. E is not related to E. So therefore, R is not reflexive. Because again, remember in the definition of reflexivity, in fact, in all three properties, the property says that it applies to all elements of the set A. But here, in this case, we found an example of an element of A that is not related to itself, right? E is not related to E, so therefore the entire relation is not reflexive. Okay, is this relation symmetric? Okay, now this is hard to see, and soon I'll show you an easier way to see this, but we're going to first show you the trickier way. So I claim that it is symmetric, since for all x and y that are elements of A, if x is related to y, and then, if x is related to y, then y is related to x. Now, if you look at these pairs, it seems reasonable, right? So like, for example, B is related to, we have B comma C, and we also have C comma B. We have C comma D, and we also have D comma C, okay, and so on. So it looks reasonable. Now, in order to really make sure, we would have to go through all possible combinations and make sure it works out. I'll show you some examples of what I mean. So we know that, well, let's think about this. Is this true? In other words, in order for R to be symmetric, we need this statement to be true. We need some other statements to be true as well, but this is one of the statements that we need to be true, right? if C is related to D, then D is related to C. Is that true? Is it true? Well, let's evaluate it. So C is related to D. Is that true? Yes, because we have C comma D. D is related to C. Is that true? Yes, because we have D comma C. So what we have is, if true, then true. Again, this is true because we have C comma D. This is true because we have D comma C. So in other words, what this conditional statement is equal to is, if true, then true. What is this equal to? True. Good. Okay, now let's check another example. How about this? If C is related to C, then C is related to C. Now notice here, X and Y are actually equal to each other. Again, we're trying to show that if X is related to Y, then Y is related to X. But nothing says that X and Y are different. So it's possible that X and Y are both C. So here's a case where X and Y are both C, both the same letter. And we want to make sure that this is true. And if C is related to C, then C is related to C. Let's see. Is this part true? C is related to C. Is that true? Yes, because we have a pair C comma C. Is this part true? Yes, because same reason, because we have this pair. So this entire expression becomes, if true, then true, which is true. So this is true. Okay, next, what about this? Is this true? Again, in order for R to be symmetric, this expression has to be true. This expression says that if C is related to E, then E is related to C. Now, is this true? Is this expression true? Well, let's break it apart. Is this part true? If C is related to E, is that true? Well, actually, it's not true because there is no pair C comma E. Now, is this true? No, because there is no pair E comma C. So this conditional becomes, if false, then false. That's what it equals to. But what is the value of if something that's false, then something that's false? So remember from our discussion of logic, this is actually true. It's a true statement. So this is a true statement. So again, it's all good so far. Now, there are many more cases that we actually would have to go through if we wanted to be really sure, but I'm not going to bother listing them all out. Okay, but if you go through, the point is, you go through all possible combinations of values from A, it should always be true that, that if X is related to Y, then Y is related to X. Okay, and therefore R is symmetric. How about transitive? Is R transitive? It is, since for every X, Y, and Z in A, if X is related to Y and Y is related to Z, then X is related to Z. Okay, now, so for example, right, so like we have B comma C and we have C comma D. So that's, and then we also have B comma D, right? So, so whatever, let's go through some examples of that. But really, we would have to check out, we would have to really verify for all examples if we want to be really sure. But I'm just going to show you some examples. So let's think about this. Again, we're trying to show that if X is related to Y and Y is related to Z, then X has to be related to Z. So I'm not going to go through all the possible examples, but just give you a flavor. So a few examples. So let's think about this. Is this expression true? Well, let's see, break it apart. So B is related to D. Is that true? Yes, we have B comma D. Okay. Is this part true? Is D related to C? Yes, it is true. So here we have, again, we have our X and our Y and our Z. Okay. And we want to make sure that B is related to C. In other words, that X is related to Z. So is this true? Oops. So sorry. So what we have is true and true. If true and true, then true. Sorry, ignore this N. I don't know where that came from. Ignore that N. Now, what is this equal to? So this is true. This evaluates the true. True and true is true. So we have if true, then true. And this evaluates to true. So this statement is true. Another example, how about this statement? Is this statement true? So here we have X is B, Y is D, and Z is B again. Okay, so you're allowed to have X and Z be the same letter. That's fine. But let's see, is this statement true? So we want to show, let's see, this is true. B is related to D. Yeah, B is related to D. Where is that? Here, B is related to D. Is D related to B? Yes, it is true. Now, is this part true? Is B related to B? Yes, it is. So what we have is if true and true, then true. That equals if true, then true, which equals true. So this statement is true. Another example. So here we have if C is related to C and C is related to C, then C is related to C. So this looks very confusing. What we're doing here is we're using the same letter for X, Y, and Z. Meaning this, we're saying, let's say we have a case where X, Y, and Z are all the same value, because nothing prevents X, Y, and Z from all being the same value. They're just elements of A. They could all be the same element of A. So again, so let's see, is this true? So let's see, this part is true, right? Because we have C comma C, and this part is true, all right? And this part is true. So what does this whole thing become? So this becomes true, and if true and true, then true, which is if true, then true, which is true. So this statement is true. How about this? So here we have X is C, Y is E, and Z is also E. Okay, and hold on, I made a mistake. All right, so again, X is C, Y is E, and then Z is E again. And so we want to show that this is true, right? Because I'm claiming that the relation is transitive. So in other words, I'm claiming that for every possible value of X, Y, and Z, if X is related to Y and Y is related to Z, then X is related to Z. So we want this to be true. So let's see, is it true though? So C is related to E. Is that true by itself? Is C related to E? No. There is no pair C comma E. How about E comma E? No. Sorry, actually, this is true. E comma E is true. So what we have is false and true. If false and true, then false. What is this equal to? So false and true becomes false. So we have if false, then false. Now, what is the value of if false, then false? Answer is true. Remember, this is stuff we learned in logic. So this statement is a true statement, which is a good thing. That means that, well, if this statement will be false, then R would not be transitive. Okay, so so we need this statement to be true in order for R to be transitive. But of course, we need all these statements to be true. And I'm not going to list out all this. There's many more statements that I haven't listed out. In other words, we need for every possible value of X, Y, and Z, for every possible combination of values for X, Y, and Z, we need to have that this is true. Let's just do one more. So how about this? B is related to E. If B is related to E and E is related to C, then B is related to C. So this here we have our X, that's B. Then we have Y, it's E, and then we have Z, which is C here. Right? So is this statement true? Well, it needs to be true if we want R to be transitive. So let's see. B is related to E. That's not true. E is related to C. That's not either true. B is related to C. That is true. So what do we have? We have if false and false, then true. That becomes if false, then true. And what is the value of that? Well, that becomes just true. So this statement is a true statement. And of course, there are going to be many more statements that we have to check out, but it's very, very tedious. And I'm going to show you in a second a much simpler way to check this. So same example, but let's as we said, R is not reflexive, but it is symmetric and transitive. And we can see this from a diagram of R. Okay, so here's a diagram of R. If we take a look at it, so notice we have 4 nodes because they are 4 elements of A. You can call each of these nodes a vertex if you wish, but they're, whatever you want to call them. And we draw an arrow every time there's an ordered pair. So we have B comma B, so we draw an arrow from B to itself. We have B comma C, so we draw an arrow from B to C. Okay, so you can go ahead and draw this entire diagram. I mean, I've drawn it out here, but you can try drawing it out yourself. But now let's take a look at this diagram. So here we can see that E is by itself, okay? And the other 3 are all connected. Now, in order for a relation to be reflexive, let's first talk about that. In order for a relation to be reflexive, you need to have one of these loops at every node, right? Because what does it mean? What does a loop at B mean? What does this loop here mean? It means that B comma B is an element of the relation, and C comma C and D comma D. But we see that at E there is no loop. That means E comma E is not an element of the relation. So therefore R is not reflexive. How about symmetric? What would symmetric say in this diagram? So in a diagram, symmetric is represented by whenever there is an arrow from one thing to another, there is an arrow going back, right? So for example, there's an arrow from C to B, and then there's an arrow going back. There's an arrow from C to D, and there's an arrow going back. There is an arrow from D to B, and there's an arrow going back from B to D, right? So, and we can see this is true for any combination of arrows. Sorry, for any combination of nodes, right? Take any 2 nodes in this diagram. If there is an arrow going from the first to the second, then there is also one going back from the second to the first. Right now, there are no arrows going to E, so we don't have to worry about arrows going from E to anyone else. But if you take any node, any 2 nodes, if there is an arrow from from the first to the second, and there's an arrow from the second to the first. All right, so that's symmetric. How about transitive? Well, transitive is represented by the idea that whenever there is an arrow from, let's say, C to B and an arrow from B to D, then there has to be an arrow directly from C to D. Again, if there is an arrow from C to B and an arrow from B to D, then there has to be an arrow from C to D directly. The idea is, if I can go from C to D like this, then I have to be able to go from C to D directly. But this is just one example. This has to work for all the nodes in the diagram. That if I can get from A to B and from B to C, then I have to be able to get from A to C directly. And that's if you look at the diagram, it does seem pretty clear that is the case. Okay, let's just give you the more the basic rules for this. So we can deduce properties of a relation R from its diagram. So right, if I give you a relation and you draw the diagram of the relation, so assuming it's a small relation where you could draw the entire diagram, so you can deduce certain properties of the relation from the diagram. In other words, you can tell from the diagram whether or not it is reflexive, whether or not it is symmetric, and whether or not it is transitive. How? So R is reflexive if every node X in the diagram has a loop, meaning every time there's a node, there's a loop at that node. Okay, so if you have a diagram where every node has a loop, then that diagram represents a relation that that is reflexive relation. That's a reflexive one. Now, if this is not the case for every node, then the relation is not reflexive, right? So in this diagram, we had one of the elements, one of the nodes did not have a loop, so therefore the relation was not reflexive. But so R is reflexive if every node X in the diagram has a loop. How about symmetric? So R is symmetric if whenever there's an arrow from X to Y, there is also an arrow going back from Y to X. Okay, that's symmetric, right? If you can go from A to B, then you have to be able to go from B to A. R is transitive if whenever you can go X to Y and Y to Z, there has to be a way of going directly from X to Z. Okay, now the thing is, it gets a little trickier. What about if you have something like this? What about if you can go from X to Y and Y back to X? Well then, so what you kind of have here is that X is, you can think of X, well, X is X, Y is Y, but then X might be Z again, right? Remember, so you can go from one to one, from here to here and from here to here, but you have to be able to go directly from X to itself. In other words, imagine X and Z are the same, right? So then what do you have? You can go from X to Y, and you can go from Y to X, but then you have to be able to go from X to itself directly. So whenever you have something like this, you need to have a loop at X. You also need to have a loop at Y, because here, Y, because if you start from, you can go from Y to X, and from X to Y, you have to be able to go from Y to itself. Anyways, if you want the relation to be transitive, then that will only be true if the diagram follows these two things, right? Whenever you have these from X to Y and from Y to Z, there has to be directly from X to Z. And then whenever you can go from X to Y and Y to Z, sorry, whenever you can go from X to Y and Y to X, you have to be able to go from X to itself directly and Y to itself directly. Now, we're going to now see some examples of proofs, formal proofs, like direct proofs, like things that we've done in the past involving relations. So here we're going to talk about a special relation, which is actually going to come up in some of the later videos in this chapter. So we start off with a natural number, right? So a number 1, 2, 3, whatever. It could be any natural number. So random, any natural number. So let n be an element of the natural numbers. In other words, what we're about to say will apply to every possible value of n. Okay. So consider the relation blank is congruent to blank mod n. This is a relation on the set Z. So what does this relation represent? Well, it tells us whether one integer is congruent to another integer mod n. Remember, n is any natural number. So we've seen this idea before, right? Where one integer is congruent to another integer mod something. So here we can think of this, if we pick any value of n, we can have the relation that tells us whether one integer is congruent to another integer mod n. This is a relation on the set of integers. It tells you whether this first integer is related to the second integer. It tells you whether they're congruent. Is this first integer congruent to the second integer mod n? Now, let us prove that this relation is a reflexive relation. Okay, now this seems really abstract, and it is very abstract, but we're going to try to prove that this relation is reflexive. So here's the proof. Well, so first, I find it helpful often when starting to write a proof to write out clearly what your goal is in the proof. What are we trying to do in this proof? So in order to show that the relation is reflexive, we have to show that for all x and z, for every integer x is congruent to x mod n, meaning x is related to itself. Right? We need to show that x is related to itself no matter what integer x is. Right? So for all x and z, x has to be congruent to x mod n. That's what we want to show. So let's do it. So first we note that no matter what natural number n is, right? N is some natural number, but it doesn't matter what it is, n divides 0. That's true because no matter what n is, well, n is certainly a natural number. It's a positive number. So even if it would be a negative number, it would also apply. So like, for example, 3 divides 0, 5 divides 0, and so on, right? Every natural number divides 0, right? Okay. So no matter what natural number n is, n divides 0. Therefore, for every integer x, we have that n divides x minus x. So why? Because x minus x is just 0. So we know that n divides 0. So therefore, n divides x minus x. But then let's remember, what's the definition of congruence? So if I know that n divides x minus x, therefore, for every integer x, we have that x is congruent to x mod n, just following the definition of congruence. Okay, so what have we proved? We have proved that for all x in z, x is congruent to x mod n. Notice we don't even know what n is, but we have proved that no matter what natural number n is, we have that for all x in z, x is congruent to x mod n. So we have shown that this relation is reflexive. Great. Now let's consider the same relation, but now let's try to prove that the relation is symmetric. So again, I'm going to write out what I'm trying to prove. We need to show that for all x and y in z, for every integer x and y, if x is congruent to y mod n, then y should be congruent to x mod n. That's what we want to show. Okay, so what we're trying to do is we're trying to prove an if-then statement. If this, then this. Okay, so we're going to use direct proof for this. So here's how we'll do it. Suppose x is congruent to y mod n. Right, so suppose the if part is true. Again, direct proof, standard direct proof. Suppose x is congruent to y mod n. So what does that tell me? So based on the definition of congruence, what that means is that n divides x minus y. Thus, based on the definition of divisibility, x minus y is equal to n times a for some integer a. Now, what I can do is multiply both sides by -1. So -1 times x minus y is equal to -1 times na. On the left side, I'm left with y minus x, right? It's -1 times x, that's negative x. And then -1 times negative y is positive y. So I have y minus x, and this is equal to n times negative a, right? I have the -1 and I could apply it to the n, or I could apply it to the a. So I'm applying it to the a. So I have n times negative a. So what do I have now? Well, I see that y minus x equals n times an integer. Negative a is an integer because I know a is an integer, so therefore negative a is also an integer. So again, I have y minus x is equal to n times some integer. Thus, based on the definition of divisibility, n divides y minus x. And therefore, based on the definition of congruence, y, whoops, I'm missing an x there. So therefore, y is congruent to x mod n. So what did we want? We wanted to show that for all x and y and z, if x is congruent to y mod n, then y is congruent to x mod n. We proved that by supposing that x is congruent to y mod n, and we concluded that y is congruent to x mod n. So we have proved what we wanted to prove. Now, most of this proof is straightforward application of definitions. The complicated part, or the tricky part, is in the middle here, where we multiply by -1. It might not seem obvious why. Well, let me try to explain. So we start off x is congruent to y mod n. Okay, then we apply the definition of that to get this. Then we apply the definition of the divisibility to get this. So at that point, we have this, x minus y is equal to NA. Now, we know, what is our goal? Our goal is to show that y is congruent to x mod n. All right, that's the then part. That's what we're trying to show. So at the end. So this is our goal. And applying the definition of congruence, we get this. And then applying the definition of divisibility, I know that I need y minus x to equal n times some integer. So that's my goal. Now I have x minus y equals something. So, but I want y minus x. Well, how can I turn x minus y into something with y minus x? Well, if you think about it a little bit, you can get that by multiplying both sides by -1, right? So you multiply this side by -1, which gives you y minus x, which is what we're looking for. And then, of course, you have to multiply the other side by -1 as well. And then you get this. And that allows you to conclude that, therefore, n divides y minus x, because, again, you have y minus x equals n times an integer. And that allows you to conclude that y is congruent to x mod n. Okay, one more proof. So the same relation, but now let's try to prove that the relation is transitive. So let's write out what we're trying to prove. We need to show that for all x, y, and z in the set Z, meaning for every integer x, y, and z, take any integers x, y, and z, if x is congruent to y mod n and y is congruent to z mod n, then x has to be congruent to z mod n. So let's prove this. So we're going to use direct proof. Suppose x is congruent to y mod n and y is congruent to z mod n. Right? X is congruent to y mod n and y is congruent to z mod n. Well, then, based on the definition of congruence, we know that n divides x minus y and n divides y minus z. Therefore, based on the definition of divisibility, we know that x minus y is equal to NA and y minus z is equal to NB for some integers a and b. Now, here's what we can do. So x minus y plus y minus z equals x minus y plus y minus z. Obviously, they're the same thing. But now we know that x minus y is equal to NA and y minus z is equal to NB. So we can rewrite this as x minus y plus y minus z, and I could remove the parentheses. They're not needed here. So I have x minus y plus y minus z. And then on this side, instead of saying x minus y, I can write NA, because I know x minus y equals NA. And instead of writing y minus z, I could write n times b, because I know that y minus z is equal to n times b. So, okay, so what do I have? I have x minus y plus y minus z is equal to NA plus NB. Now, on the left side, this simplifies to x minus z, because the negative y and the positive y cancel each other out. So I have x minus z, and this is equal to n times, and I could factor, so I factor out the n times a plus b. So now what do I have? Well, I have that x minus z is equal to n times an integer. N times an integer. A plus b is an integer. Thus, n divides x minus z based on the definition of divisibility. Right? Just applying that, we have x minus z is equal to n times an integer. So therefore, n divides x minus z. And therefore, x is congruent to z mod n. So what did we do? We said, suppose x is congruent to y mod n and y is congruent to z mod n, meaning suppose the if part is true. And we concluded that therefore the then part must be true, that x is congruent to z mod n. So we have proved that this relation is, in fact, transitive.